Hey everybody. So this week in class, we learned about how to find the effect of X on Y instead of just say like the correlation between X and Y. We talked about two different ways to do that. The first way of finding the effect of X on Y is to randomize X. So this was kind of doing an experiment. This was random assignment of X. So if you have a random assignment of X, then all of the things we learned in lecture 2, just doing the difference of mean tests, you can just do those, and now you'll have a causal interpretation of the effect of X on Y instead of just the correlation between X and Y. So I'm not going to spend any time on sort of random assignment in this R coding lecture, because that's kind of a property of the data. It's not anything different about how you would do your t-test. So what we will focus on in this lecture instead is causal matching. So that was our second way of finding the effect of X on Y. Now, if X is not randomly assigned, if X is, like college attendance or doctor visits, say it's like the result of a choice, then you can't interpret the conditional mean difference as the causal effect. But if you say match your treated units who have X equals 1 with control units who have X equals 0, and that look very similar in all of the observable dimensions, then you'll be able to say the conditional mean difference is at least closer to being causal. So the package that we're going to need is called MatchIt. So this is the name of it, MatchIt. So I'm using in the console to install this package. This is maybe a kind of different way of installing, as opposed to going to the right here, going to packages and clicking install. So I'll just show you how this works. You should just hit enter, and then it's going to show you a bunch of status updates, and it'll say, okay, like you have, in my case, I already have MatchIt installed, so it's not going to install. But for you, it should just say, yeah, it's installing, and then successfully installed. All right, and now we'll open up a new R script. Okay, so we're going to need our typical packages, tidyverse, ggplot, but then we'll also need this new package of MatchIt. Okay, perfect. So the data set that we used for an example in class on the job training is actually included in the MatchIt package. So if you run, if you load up these libraries, and then you run the following command, then you're going to see in the upper right, you have this thing, values Lalonde. Lalonde is the name of our data set. Okay, so we can take a look at it. Here it is. So this is a data set where we have several variables. We have treatment, so treat, that's going to be the variable that's 0, 1. That's our X variable corresponding to whether or not someone has received on-the-job training, someone's age in years, their education level in years, their race. It's going to be either Black, Hispanic, or white in this data set. We have whether they're married or not, whether they have no degree, or whether they do have a degree. And then we have on the far right, RE78. So that's going to be people's income, yearly income in 1978, which is when this data is from. Okay, so that's what's going on in the data set there. So if you want to access this data set, right, it's stored under the name Lalonde once you've run this command on line 7. Now you'll notice that when we look at this data set, it looks a little different than the other data sets we've done. That's because when we loaded the other data sets in previous lectures, we used read_CSV, and it loaded them as kind of a slightly modified style of data set called a tibble. So we can run this command. And then if we take a look at Lalonde, you're going to see like, oh, okay, this is kind of what we've been expecting when we look at a data set, right? We see like the dimensions here. We have our variable names. We have the type of variable. And then we have kind of a little snapshot of the values up to the first 10 rows, okay? Perfect, so that's our data set. Now, what we need to do, first, we can just run a t-test looking at the effect of on-the-job training on income. So we know how to do that. There's our y variable income. Here's our x variable on-the-job training. Our data is this Lalonde data set. And if we run this, then we'll see that we have a p-value of 0.35. So we're going to fail to reject the null of equal means. We're going to see that in group 1, the group that received on-the-job training, the average income is $6,300 per year. And in group 0 that did not receive training, the income is actually higher. It's $6,900 per year. All right. So what this initial t-test is saying is, the effect is insignificant, and we have a lower average income in the group that received treatment. Not what you'd expect, right? On-the-job training should boost your income. However, on-the-job training is not being randomly assigned in this data set, right? You can imagine that the people who are receiving on-the-job training look very different. There's a selection bias, okay? So what we're going to do is we're going to use the MatchIt function. And when you kind of write out this function, MatchIt, you're going to see a few prompts. The first one is for a formula. So for the formula for MatchIt, what it wants is the variable, the treatment variable, which is the x variable first. And then after the tilde, it wants all of the observable covariates that you want to match on. So this is all the covariates that you want to kind of be equalized between the treated and control group, okay? So let's take a look at our table again, all the different variables in it. All right, so we have, okay, we're going to want to match on age. We'll match on education. We'll match on race. We'll match on marital status. And we'll match on this no degree variable, okay? So what we want is, what we're saying with this formula is across our treatment and our control groups. So for treat equal 1 and treat equal 0, we want these 5 variables to be equalized, okay? So we'll specify the data. All right, and now we need to specify a few other things, right? So MatchIt is a very powerful function. It can do matching in a lot of different ways. In class, what we focused on was called coarsened exact matching. So for method, we're going to put CEM, right? Now, if you look at the help document for the function MatchIt, you'll see a bunch of stuff comes up. And you can see, all right, there's formula, data, and then method is what we just specified. So let's go and take a look at this method section. So there's a bunch of different allowed methods. Nearest neighbor, that's for propensity scores. We talked about that at the very end of the lecture. Something called genetic matching. There's CEM, coarse and exact matching. There's exact matching, like we talked about, and which we ruled out as being too kind of strict. So there's a ton of different matching. So CEM is what we learned about, and that's what we'll focus on. But if you want to learn about the other ones, you're certainly welcome to. Okay. So we'll specify that method is CEM. We're going to specify another argument, which is K2K. We're going to specify that as being true. Now, what K2K says is for every treated unit, every unit with x equals 1, we're going to find exactly 1 unit with x equals 0. There might be multiple units, x equals 0 units, that match the same treated one. So we're just going to randomly, this argument says, let's randomly pick just one of those treated, or one of those control unit that matches on these coarsened variables are treated unit. Okay. Good. So we have CM, we have K2K equals true. Okay, so do we need anything else? I don't think so. Oh yes, no, we do need one more thing. So in class, I said we need to specify how many cut points we want for our variables for the coarsening, right? And what do I mean by that? Well, if you look at the age variable, you can see it's kind of a bunch of different numbers, right? It's, you know, we can see values ranging from 22 up through 37 here. So we're not going to match exactly on age. We're going to divide age into a certain number of buckets. And then within each bucket, we'll match exactly within that bucket, right? So a bucket could be people from 22 to 25 years old, in which case anyone who has an age from 22 to 25 would be in that bucket, and so on and so forth. So MatchIt just wants you to specify the number of cut points. So if you specify 3 cut points, for instance, it's going to divide the range of that variable into 4, right? So 3 cut points will divide it into 4 segments. And then within each segment, that's kind of how it's going to match, right? Perfect. So we're going to store the output of this function in a variable, and then we're going to run it. Okay, so we run it. We see this thing match underscore out, right? And now we can take a look at it. So the first thing that we can do is summary. So if we run this command, what we can see is a ton of information has been output. Let's take a close look at it. So we've got our initial call, our initial formula. And then what we can see is this first block of data is the summary of balance for all data. This is our unmatched sample. So it's going to show you the mean age for treated units, and then the mean age for control units. And you can see that they're different. And then in the next column, it's going to show you the standardized mean difference. So that's going to be the treated mean minus the control mean divided by the standard deviation of age for the treated subsample. The other stuff, the other columns, you can ignore. Okay, good. The second chunk is the summary of balance for the matched data. So that's going to show you all the same means, except now we're just looking at the subset of data where we have a treated unit matched with a control unit, meaning that that treated unit has the exact same coarsened matching variables as the control unit. Okay. Now we use the coarsened variables to match treated and control. But when we take these averages, these are just kind of the baseline variables. So we're saying just the average age within the matched treated units and the average age within the matched control units, and then the standardized mean differences. Okay, good. So you'll notice that we have age, education, we have married and no degree, but then we have these kind of 3 new variables. So the variable that we matched on was race. However, we now have race black, race Hispanic, and race white. That's because race is a categorical variable. So race takes 3 unique unordered values. So the way that R deals with that is by splitting these into so-called dummy variables. So race black, that's going to be a new variable that R has created that equals 1 if that categorical variable race equals black for that observation. Okay, so you can see in this average number, so race black being 0.72, that means that in the matched treated units, 72% or a share of 72 people are black. Okay, whereas in the unmatched units, 84% of treated units are black. Okay, perfect. And you can see that we also have those averages for Hispanic and for white. All right, and then at the very bottom, we see sample sizes. So all means, again, like sort of the total unmatched sample, we have 429 controls to start with and 185 treated. Once we match, we can only match 105 treated units. So only for 105 treated units is there a control unit out there that has the exact same coarsened variables, okay? So we have 105 treated and then 105 control, 1-to-1, and so we've kind of not been able to match some of our units. So 324 is just 429 minus 105, right? From the total amount of control minus the control that actually got matched, that gives us kind of the ones that are left over. These unmatched do not play any role in the analysis. Once you have your matched sample, that's what you're. Another way to visualize this data we saw in class was with the so-called love plot. And to create the love plot, all you need to do is use this command plot around the summary, right? If you run this, then what you're going to see is on the y-axis all the names of our covariates. On the x-axis, you have the absolute standardized mean difference. So that is going to be the number corresponding to the column, like this third column. And then you have black points and you have unfilled points. So the filled points, that's the standardized mean difference in the matched sample. And the unfilled points, those are the standardized mean differences in the unmatched or total sample. All right. So what you can see is that anytime you kind of have the unfilled point to the right of the filled point, that means the standardized mean difference in the total sample is larger. That means it's like less balanced, right? As you go left, right, these filled points, it's a smaller standardized mean difference, okay? So these vertical lines, the dashed one is 0.05, the solid one is 0.1. So those are our thresholds for like good balance, right? And we can see actually that for our race variable, our dummies, and then for married and no degree, we're actually like perfect balance. So these variables, we've been able to kind of match them perfectly, which is not always the case. Usually you're not going to see like a perfect match like this for any variable. Usually you're just hoping that the filled points kind of become a lot smaller for better balance and are below these thresholds of 0.05 and 0.1. Right? So you can see that age is not below 0.1. And that's just something that we kind of have to deal with right now. In a few minutes, I'll show maybe there's something that we can do. Okay. So notice this looks a little bit different than what we have in class. That's because this is the absolute standardized mean difference. If we set abs equals false, then we have just the standardized mean difference. And so instead of taking the absolute value and making everything positive, this shows kind of like whether the standardized mean difference is negative or positive, okay? So you can use either one of these. I kind of prefer standardized mean difference because it shows more information, right? It shows whether the treated individuals had kind of like a lower average or a higher average for any particular value, right? If the standardized mean difference is negative, the treated individuals have a lower average value for that variable. And the standardized mean difference positive, the treated individuals have a higher average for that variable compared to the control. All right, perfect. So we now have our kind of plots like we're showing, all right, coarsened exact matching, balance has improved. So the next thing we're going to do is actually recover our match data. So I'm going to call it matched Lalonde. And this match data function, you just apply it to the output of this MatchIt function on line 12. And that should, maybe it's a period. Yeah. So that's going to give us this thing match Lalonde in the upper right here. It says now we have 210 observations of 11 variables. So let's take a look at this. It's got all of the variables that we had before, but we only have 210 observations. Why 210? It's because we have 105 treated and 105 control in our matched sample. So 105 plus 105 is 210. We have a few other columns that have appeared. We have this thing called weights. With the command that I've specified for you, weights is always going to be equal to 1. So don't worry about that right now. And then we also have this thing subclass. Subclass shows you which variables are matched or which observations are matched with each other. So if we sort on subclass, you'll see subclass, it's always a pair of numbers, 1, 1, 2, 2, 3, 3. So 1, 1, this says that we've got a treated unit and then we have a control unit. And you can see the age, you can see the education, race, and then married, no degree. So these things are kind of like the two variables. So this is kind of like the balanced control unit for that treatment unit. Okay. So you'll notice for the variable married and for no degree and for race, it's always going to be an exact match when you look at within each subclass. Why? Well, when you look at our standardized mean difference, you'll see like the race, whether or not they're married and whether or not they have a degree, the difference is 0. Okay. So because the difference is 0, that's telling us like it's exact matches for those variables. Okay. Perfect. So that's our match data. And now we can just run a t-test using the same variables, income on treatment, but now data instead of Lalonde is matched Lalonde. Okay. And now we can see here. So let's look at the means first. We can see the mean in group 1, the treated group, is 6,201. And then for group 0, it's 5,400. So now with matching, it looks like training improves income, at least with the difference in means. And you'd say, okay, yeah, that would be a causal effect. However, when you look at the t-stat and when you look at the p-value, you can see the p is not less than 0.05. So we still fail to reject the null of equal means. Okay. So what matching did here was it kind of created a matched sample where it held all these covariates constant, which could have been leading to selection bias and leading to like, an incorrect effect of job training on income. So we kind of control for all those things. So now we have like just the effect of job training on income as opposed to the effect of all these other things changing in the background. So we found that, oh yeah, job training, it does help income, but it's not significant. So we actually can't conclude that. We fail to reject the null, right? Perfect. So, one thing you might be concerned, you might be wondering, it's like, oh, well, when we look at our, oh, and yeah, once you have this t-test, like, of course, you can do the usual stuff that we learned in the second lecture. Like you can create a graph, you can plot the two bars for the difference in means. So I'll let you kind of think about, or yeah, I'll let you guys do that on your own. Here, though, you might think, okay, like when we did the matching, we lost a lot of data, right? We went from 185 treated units to 105. So maybe our coarsening was too fine. If our coarsening is too fine, then we drop a lot of observations because we just can't find a good enough match. So let's try fewer cut points, which leads to bigger buckets for those observable covariates, which means it's like easier to match. I'm gonna call this match out 2. And when we do this one, what we should see is that we have more observations, right? Actually, we don't. So we actually have 105. Okay, that can happen sometimes. All right. So let's go to just a single cut point. All right, so that one didn't work. So it looks kind of actually like maybe 3 cut points is the best we can do in terms of keeping our sample somewhat large. One thing I want to point out is with, say, like 5 cut points, you'll notice that we start to drop observations because we have these like much finer buckets that we want to do matching in. If we increase the cut points even further, we're going to keep dropping observations. Right now, we only have 77 treated units that we can find a match for. Okay. Maybe that like with these better matches, somehow we could get a more precise causal estimate. So let's just check that out. So we have our matched data set with these finer cut points. And then we do a t-test. All right. Yeah, so what we find is, yeah, it's still the case that the mean in group 1 is larger. So, you know, on the job training leads to a higher sample average, but the p-value is still greater than 0.05. Okay. So it seems like, you know, maybe this data set is just too small to have a precise answer to this. Or maybe there is truly no effect of on-the-job training. All right. So that's everything that you should need for this week's coding component of your assignment. So I'll leave it at that. And of course, if you have any questions, feel free to contact me by email or come to office hours.